You know, I once got a letter from a student who asked me, Professor Feynman, if I could travel back in time and kill my grandfather before my father was born, would I cease to exist? And I wrote back, that's a hell of a question, but here's a better one. If you did cease to exist, who killed your grandfather? The student never wrote back. Maybe he's still thinking about it. Or maybe he went back in time and got himself into trouble. Time travel. It sounds like science fiction, doesn't it? Like something out of H.G. Wells. But here's the thing that'll really bake your noodle. According to the laws of physics as we understand them today, time travel isn't just possible. In some ways, it's inevitable. You're doing it right now. We all are. The question isn't really, is time travel possible? The question is, what kind of time travel is possible? And more importantly, why the hell does the universe work this way? So let me tell you a story about time, about Einstein, about some very confused particles, and about why you, yes, you, are a time traveler whether you like it or not. Before we can talk about traveling through time, we need to understand what time actually is. And I'll tell you right now, it's not what you think. When I was a kid in Far Rockaway, my father gave me a clock, not to tell time, to take apart. And when I opened it up, I saw all these gears and springs, tick, tick, ticking away. And I asked him, Pop, what makes time? He said, the gears, Richard, the gears make the clock go. And I said, no, not the clock. What makes time? He looked at me for a long moment and said, that's the question, isn't it? You see, we think of time like a river that flows in one direction, from the past, through the present, into the future. But that's not quite right. Einstein showed us something much stranger. Imagine you're sitting in a train station. A train goes by at tremendous speed, say close to the speed of light. Now there's a passenger on that train and she's bouncing a ball, up and down, up and down. To her, the ball is just going straight up and straight down. But to you, watching from the platform, that ball isn't going straight up and down at all. It's going up and down and forward, tracing out a diagonal path through space. Same ball, same bounce, two completely different observations. And here's the kicker. You're both right. Now, if space can look different depending on how you're moving through it, Einstein asked, why should time be any different? And that simple question, that one little question, changed everything. Time isn't a river that flows the same for everyone. Time is, well, it's more like a dimension, like length or width or height. And just like you can measure different lengths depending on your perspective, you can measure different times depending on how fast you're moving. This isn't philosophy. This isn't metaphysics. This is cold, hard, experimentally verified physics. In 1905, what we call Einstein's miracle year, he published a paper with a boring title, On the Electrodynamics of Moving Bodies. Boring title, earth-shattering content. Einstein realized that the speed of light is the same for everyone, no matter how fast they're moving. That doesn't sound revolutionary until you think about it for more than 5 seconds. If you're on a train going 99% of the speed of light and you turn on a flashlight, you'd expect the light to go 99% plus the speed of light. But it doesn't. It just goes the speed of light, the same speed it would go if you were standing still. How is that possible?
Einstein's answer? Because time itself slows down for you when you move faster. Let me say that again, because it's important. Time itself slows down. This isn't an illusion. This isn't a trick. Your watch actually ticks slower. Your heart actually beats slower. You actually age slower. We call this time dilation. And it's not a theory anymore. It's a fact. We've measured it. We've tested it. It's real. There are particles called muons that rain down on us from space, created when cosmic rays hit our atmosphere. These muons are unstable. They decay in about 2 millionths of a second. Given how fast they're moving and how far they have to travel, most of them should decay before they reach the ground. But they don't. Far more of them reach the ground than should be possible. Why? Because from our perspective, time is running normally. But from the muon's perspective, traveling at 99.8% of the speed of light, Time is running much slower. Only a tiny fraction of a second has passed for the muon, while microseconds have passed for us. The muon has traveled into our future. It's a time traveler. And this happens billions of times a day, all over the Earth. Now here's where it gets really weird. Let me tell you about the twin paradox. Imagine you have two twins. Let's call them Alice and Bob. Alice stays on Earth. Bob gets in a spaceship and zooms off at 99.5% of the speed of light. He travels for what feels to him like 1 year, then turns around and comes back. Another year for him. 2 years total. But when he gets back to Earth and climbs out of his spaceship, his twin sister Alice isn't 2 years older. She's 20 years older. Bob has traveled into the future. He's aged 2 years, while the rest of the universe aged 20. And this isn't science fiction. This is what Einstein's equations predict, and it's what every experiment confirms. Now, you might ask, wait a minute, Feynman, if all motion is relative, couldn't we say that Bob was sitting still and the Earth was moving? Wouldn't that mean Alice should be younger? Excellent question. And the answer is no, because Bob accelerated. He turned around. He felt forces that Alice didn't feel. The situation isn't symmetric. Bob did something different, and the universe keeps score. This is real. The GPS satellites orbiting Earth right now are traveling fast enough that their clocks run slightly slower than ours. Not by much, only about 38 microseconds per day, but it's measurable. If we didn't correct for time dilation, your GPS would be off by miles within a day. You want proof that time travel is real? Pull out your phone. Check your location. Congratulations, you're using relativity. You're using time travel technology. But wait, there's more, and it gets stranger. Speed isn't the only thing that affects time. Gravity does too. Einstein's general theory of relativity, published in 1915, showed us that massive objects like stars and planets don't just sit in space, they bend space, they curve it, like a bowling ball on a trampoline. And if massive objects bend space, they also bend time. The stronger the gravity, the slower time runs. If you're standing at sea level, time runs slightly faster than it does in a basement. Not by much, we're talking nanoseconds, but it's real. We've measured it with atomic clocks.
Now imagine something with gravity so intense that it bends space-time into a deep, deep well. Something like a black hole. Near a black hole, time slows to a crawl. If you watched someone fall into a black hole from a safe distance, you'd see them slow down, slow down, slow down, getting closer and closer to the edge, but never quite reaching it. They'd appear to freeze in time, but from their perspective, they'd fall right in, screaming all the way. No hesitation, no slowdown. They'd experience time normally. Same event, two completely different experiences of time. There's a beautiful and terrifying scene in the movie Interstellar, where the astronauts land on a planet near a black hole. They spend a few hours there, and when they return to their ship, they find that 23 years have passed for the crew member who stayed behind. That's not Hollywood magic. That's Einstein. That's real physics. If you wanted to travel far into Earth's future, say 1,000 years, you wouldn't need a time machine. You just need a spaceship and a black hole. Orbit close to the event horizon for a few hours, then come home. Everyone you knew would be long dead, but you'd have traveled to the future. One-way ticket, though. That's the catch. So, we can travel to the future, that's established. Speed does it, gravity does it. We've measured it, tested it, used it in technology. But what about going backwards? That's what everyone really wants to know, isn't it? Can we go back to the past? This is where things get complicated. Einstein's equations don't forbid it. In fact, they contain solutions, weird, exotic solutions, that allow for what we call closed time-like curves. Fancy words for paths through space-time that loop back on themselves. In 1949, Kurt Gödel, the same Gödel famous for his incompleteness theorems in mathematics,
found a solution to Einstein's equations that described a rotating universe. And in this universe, if you traveled in a big enough circle, you could arrive back at your starting point before you left. You could meet yourself. You could shake your own hand. You could attend your own birth. And Gödel wasn't some crackpot. He was Einstein's walking companion at Princeton. They'd stroll around campus together talking about physics. Einstein called him the greatest logician since Aristotle. Later, physicists found other solutions: rotating black holes, cosmic strings, wormholes. All of them theoretically could allow travel to the past. But, and this is a big but, every single one of these solutions requires something that probably doesn't exist: exotic matter with negative energy, or infinitely long rotating cylinders, or other things that make the universe look very different from the one we actually live in. It's like finding a solution to an equation that says x equals -1, and then discovering that x represents the number of apples in a basket. Sure, mathematically it works, but physically, not so much.
And even if we could go back in time, we'd run into these damn paradoxes. And they're not just philosophical puzzles. They're serious problems that tell us something deep about how the universe works. The most famous is the grandfather paradox, which I mentioned at the start. If you go back in time and kill your grandfather before your father is born, then your father is never born, so you're never born, so you can't go back to kill your grandfather, so your grandfather lives, so your father is born, so you are born, so you do go back to kill your grandfather, so you see the problem. Some people try to get around this with the multiple timelines idea, that when you go back and change something, you create a new timeline, a parallel universe. But that's just moving the problem around. Where do these new universes come from? What determines which one you end up in? It raises more questions than it answers. Others say the universe must be self-consistent, that you can go back in time, but you can't change anything that would create a paradox. If you try to kill your grandfather, something will always stop you. Your gun will jam, you'll trip, a bird will fly into your face. This is called the Novikov self-consistency principle. It's named after Igor Novikov, a Russian physicist who proposed that the universe has a kind of cosmic censorship that prevents paradoxes. But here's what really bothers me about all of this. If the universe has to bend over backwards to prevent paradoxes, doesn't that suggest that backward time travel is, well, unnatural? That the universe is trying to tell us something? Maybe the real answer is simpler. Maybe the laws of physics, as we understand them, allow for backward time travel in theory, but something we don't understand yet makes it impossible in practice. Maybe there's a law we haven't discovered, a principle that says the future can influence the past in certain limited ways, like particles in quantum mechanics, but you can't send information backward in time. You can't send yourself backward in time. You can't create paradoxes. And speaking of quantum mechanics, oh boy, does that complicate things. In the quantum world, particles don't have definite positions or velocities until you measure them. They exist in superposition, kind of being in multiple places at once. And somehow, when you measure them, they choose one state. But here's the weird part. The math of quantum mechanics is perfectly reversible. If you could run time backward, all the quantum equations would still work. There's nothing in quantum mechanics that says time has a preferred direction, and yet we experience time as having a direction. We remember the past, not the future. Eggs break but don't unbreak. Milk mixes into coffee but doesn't unmix. Why? Why does time have an arrow? The answer seems to be entropy. Disorder. The second law of thermodynamics says that entropy always increases. Things get messier, not neater. That's why you can turn an egg into an omelet, but not an omelet into an egg. But here's what's strange. That's a statistical law, not a fundamental one. It's not impossible for an omelet to spontaneously reassemble into an egg. It's just incredibly, ridiculously, absurdly unlikely. So unlikely that it would never happen in the entire age of the universe, but not forbidden. And that raises a question.
If the fundamental laws of physics are time-symmetric, why does the universe have an arrow of time at all? Maybe it has to do with the Big Bang. Maybe the universe started in an incredibly low entropy state, highly ordered, and it's been running downhill ever since, getting messier and messier. But why did it start that way? We don't know. So, is time travel possible? Forward time travel? Absolutely. You're doing it right now. Speed it up, get near a black hole, or just be patient, you'll get to the future eventually. Backward time travel? Maybe. The equations don't forbid it, but the universe seems to. Every time we find a way it might work, we find a reason it probably doesn't. Paradoxes, energy requirements, the universe's apparent allergy to self-contradiction. My hunch is the universe is trying to tell us something, and that something is probably you can look forward but not back. You can remember the past, but you can't change it. You can influence the future, but you can't know it. Why? I don't know. Maybe it's fundamental to the way causality works. Maybe there's a deeper law we haven't discovered yet. But here's what I do know. The fact that we can even ask these questions, that we can use mathematics and experiments to explore them, that's incredible. 100 years ago, time travel was pure fantasy. Today, it's physics. We've measured time dilation. We've seen it in particles. We've used it in technology. And who knows? Maybe in another 100 years, someone will figure out something we missed. Maybe they'll find a loophole, a way to thread the needle through the paradoxes. Or maybe not. Maybe the universe has drawn a line and said, this far, no further. But either way, the journey to find out, that's the adventure. That's what makes physics beautiful. You know what I love about the universe? It's not obligated to make sense to you. It doesn't care what you think should be possible. It just is what it is. And our job as physicists, as curious humans, is to figure out what that is. Time travel to the future? Confirmed. Time travel to the past? TBD. But the fact that we're even having this conversation, that we've gone from time is absolute to time is relative in just over a century, that tells me we've barely scratched the surface of what's possible. So keep asking questions, keep being curious, keep wondering what's really going on beneath the surface of reality. Because if there's one thing I've learned in my years doing physics, it's this. The universe is always stranger than we imagine. And that's the best news I can give you. Now, if you'll excuse me,